if I have a noisy operation of the gate, of the Clifford gate, for example, this could be a controlled knot between two qubits, I'm going to use a representation of the noise in which I first apply a noise channel, and then I apply the ideal gate. Okay, so if you want, this applies a circuit. These are, say, two qubits. This is a C naught, for example. So I'll first apply my channel, okay, lambda. This is a noisy channel. And then I'll apply this G, the C naught, for example. But this is a perfect C naught, okay, in this representation. Okay? So this is just a way to represent noise. It's a very general representation. I think, except for some very pathological cases, this is a completely general equation which I can solve. I can always use this representation to represent my noisy gates. Okay, so this is one thing that's important to discuss. And then the next thing I want to discuss is something I started yesterday, is to discuss Pauli channels. So Pauli channels are going to be an important class of channels. You'll soon see why. Let me just define first what it is. So a Pauli channel is the following. So acting, say, on the density matrix. This channel, is a sum of probabilities, P alpha. And then I'm going to sandwich my operator, my, say, density operator, between two Paulis, which are the same. Okay? So this is a Pauli channel. And we also discussed yesterday that the matrix form for representing this channel is a diagonal matrix. Let's see why. What happens if I take this channel and I apply it on a Pauli PB? Okay, so let's insert this Pauli PB into this definition here. Okay, so I'll have a sum over alpha, P alpha PB, P alpha. Okay? So what can this multiplication of Pauli operators be? There's two options. For each alpha, there are two possible options. Either P alpha commutes with PB, or it doesn't commute, right? So I'm going to write it like this. So if P alpha and PB commute, then this is just PB to the power 3. Okay, PB squared. P squared is always 1. So if P alpha and PB commute, meaning that this is the same Pauli operator, meaning that basically you get P squared times PB, okay? So then I just get PB back. But if they anti-commute, then I get minus PB. Okay, so this is, I'm going to write this as a sum of P alpha minus 1 to the power alpha B. I should have used A here. Sorry, switch so I don't get confused. I'm going to switch the notation. Okay, so I'm going to write it like this. And this number here, okay, A comma B, is just going to be 0 if PA and PB commute. And it's going to be 1 if PA and PB anti-commute. Okay? Yes. Let me just, yeah. Okay?
You just give the notation of alpha and A. They are the same?
Yeah, sorry. Yes. I mean, it's when I sum on an index, it could be whatever. Nice to use the same thing. Okay? So, but you see, so this is why it's a diagonal channel, because I put PB in here, and I get PB out times factor. Okay? So basically, the matrix representation of this channel is diagonal, and it's going to be 1 lambda A, A1, and A basically 2 to the n or 4 to the n. Okay, so it's a diagonal channel. And the relation between the lambda and the p's, as we just saw here, lambda B, is equal to sum over all the a's minus 1 to the power A comma B times P A. This is the transformation between the P and the lambda. This is sometimes called the Walsh-Hadamard transform. I don't know who Walsh is. Okay, and by the way, also the inverse is also possible. So the inverse transformation, I think this is with 4 to the n, is sum over b. Okay, so this is the inverse transformation. So this is our Pauli. This is the definition of a Pauli chain. Yeah. You don't see what I'm writing. So what? Okay. So should I write? This is the no zone, no fly zone. Okay. So okay. So I'm just going to rewrite. So my matrix lambda is diagonal. Okay, and this lambda a this is what you just see here. The, lambda b is sum over a p a. Okay, this is the relation between the lambdas and the p's. Okay, so pa is the definition of the channel. Okay, well I should switch to a here. Okay. Here, so let's thank you. That's actually a good remark. So use small p and large p. Okay. Thing is, it's annoying to kind of tick all those p's here. Okay. Is that clear? Okay. So why do I like Pauli channels? Remember from yesterday why these noise channels are nice? It's because if I have a circuit that's only composed of Pauli channels and Clifford, it could be a many-body quantum circuit. If the only thing I have is Pauli channels and Clifford gates, perfect Clifford gates, then I can compute the outcome of this channel very easily. It's not a big computational problem. I don't need to multiply large matrices. It's just because, as we remember, if G is Clifford, for a Clifford gate, G acting on, this is a super operator, G acting on some Pauli, A, will give me some other Pauli. Maybe the same, maybe different. Okay? So, and then, what? With weight 1. That's the Clifford operation. Okay? And moreover, and these lambdas are diagonal. Okay? They're diagonal on the Clifford basis, so it's not a problem for me to keep track of a circuit that basically propagate a Pauli through the circuit. Okay, so this is sometimes called the Neal-Naflam theorem, saying that basically any Clifford operations are, if you have a quantum computer that can only do Clifford operations, okay, then it's simulable by a classical computer, just because I can just keep track of these Paulis, right? The whole circuit is composed of these G's, right? Then I can just keep track of what happens to my Pauli basis at each step, and it's just very easy calculation. No, but all I need to keep is a bit. No, but I just need to keep a bit string. So if I want to compute some expectation value, I can just propagate it through the circuit. Okay? So, and I just need to basically keep track of this bit string. And the fact that I'm adding these noise channels, they're Pauli channels, doesn't complicate things substantially because they're diagonal in the Pauli basis. So it's okay? So the argument is clear? So Pauli channels are good, okay? But yesterday, somebody at the end of the talk asked me a very important question. Is actual quantum computers, can the noise in actual quantum computers be described by Pauli channels? And the answer is no, okay? So then you have to ask me, why am I wasting your time with this definition, right? Okay? So it turns out it's true that the noise in actual quantum computers is not described by Pauli channels, but I'm now going to show you a method to force it to be Pauli channels, okay? Okay? And this method, so can I erase this? Okay, this definition. So this method goes by 2 different names, depending on which company implements it. called either Pauli twirling, or it's called also randomized compiling.
Which companies are you referring to?
Not, either IBM, for example, or Keysight, that would be different language. Okay? Okay, but this was just a joke. These two names are basically describing the same thing. Okay? So and I'm going to show you basically this method takes any noise channel, any noise description of your quantum computer and turns it into a Pauli channel. Okay? So it is what's written there. It's a way to recompile the quantum circuit. Okay? So let's see how it works. Okay? So I'm going to define if for a quantum process lambda, define its twirl, its Pauli twirl, in the following way. Okay, so we're going to first write it in super operator language and then in regular kind of operator language. So in super operator language, lambda tilde, the twirl version of lambda, okay, is going to be sum over a. Okay, so sorry, it's first there's some normalization factor, which is just the number of elements, number of possible Pauli strings. Okay, so this is what P is. And then I'm going to sum over A. Okay, and then I'm going to first apply a random Pauli A, apply my map, and then apply this random Pauli again. Okay, so if I think about a quantum channel, okay, so I have my noise. So for now, I'm thinking about the gate as if the gate was, remember we wanted to apply a gate G. I mean, our representation of the noisy gate was a gate G and then a lambda, right? This was my description of the gate. So for now, I'm going to take G equals to identity, and I'm going to show the general case in a second. So just let's assume that G is equal to identity, so I only have lambda.
Why did you switch notation? Previously, Pauli was...
No, this is a super operator pi. So this is...
the same Pauli.
So I'll write in a second, it'll be clear in a second, okay? Yeah, it's a Pauli, but it's a super operator for conjugating with a Pauli. Okay, let me write this. So just before I do that, so I'm going to give up on this G for a second. Okay, and what this tells me to do is basically in my circuit is just apply random Paulis before and after my operation. Okay, so just choose a random Pauli here and apply it here and here. Let me write it in a different way, and then it will be clear.
When you talked about Pauli, it was a many-qubit operation.
Yeah. Right. This is a many-qubit Pauli.
So why did you
But this is a Pauli. Any single qubit Pauli is a multiplication over all the qubits, J, right? P, A, right? Some Pauli string. For example, let's do some. Let's do this one. So if I have two qubits, right, then P, some P, specific P, for example, would be, I don't know, X on qubit 1 and Z on qubit 2. This would be some specific P. Okay? So I'm going to do X on qubit 1, Z on qubit 2, X on qubit 1, Z on qubit 2. This would be basically applying this pound. Okay? So I'm going to first apply random Pauli, and then apply it again after the channel. Okay? So let me rewrite this differently. So the channel acting on this twirl channel, acting on a state rho, okay, is going to be basically okay, sum over A, PA, this channel, okay. So I'm first acting with my P, my first P. This is P. A, both of these, okay, acting on rho, acting with the channel, and then acting with PA again. Okay? So these two things are equivalent. This is why I use the notation pi here, because pi is the super operator corresponding to a conjugation. Okay? Is this clear? No? Okay, so if I erase this, you're happy? So I first apply, I take my state, I first apply PA. This is PA. It says x1, z2. Okay, but I conjugate it because it's an operator. Okay, so I conjugate it. Then I apply the map, lambda. Okay, and then I apply the same thing afterwards. Okay?
So it's a single Pauli string.
This is a single Pauli string, and this is the same single Pauli. It's a string of single Paulis.
So on the right, you wrote the product of the J.
That's right. I mean, here, okay. Yeah. Yeah, so sorry. I should have wrote, yeah, I abused the notation here. Yeah. Okay.
And also normalized by 1.
Yeah, thank you. It should be normalized by 1. So you see the sum here is basically sample from the distribution over Paulis with equal weight. So it's probability distribution of or all possible Pauli strings with equal weight, right? Because you see the sum has equal weights for all Paulis, right? And this is just a normalization factor that normalizes the distribution. Okay? So you flip a coin, apply according to, it's a 4 to the n sided coin, you apply the Pauli, okay? And then you apply it again. Okay? Okay, so the claim is that this now, after I've done this, okay, after I basically sampled over all possible Pauli strings, I now have lambda tilde, this twirled version, is a Pauli channel. Acting on rho, okay? So let me show you why this is the case, okay? If you take one thing out of this talk, will be this. Okay, so, yeah, this here. Okay, so I'm now going to compute this, okay, and show you that it's a Pauli channel directly, okay? This result actually follows from some much more general result in group theory. It's called Schur's lemma, but I'm a pedestrian, okay? So I'm just going to compute it for you, okay? So remember that I'm now going to use the Krauss representation, okay, of a super operator. I don't remember if I put the dagger on the left or on the right last time, but in any case. Okay? So I'm going to use this, and I'm going to put this in here. So basically, my twirled lambda is a sum over A and B. Sorry, it's a sum over, yeah, A, J. P, A, K, J, dagger, P, A, rho, P, A. So far, is that okay? Yeah? What? I put 2 daggers. I knew. Sorry about that. Okay? So now, I need to do one more step. So actually, let me just look at a specific J here, and I want to expand this matrix in some basis. Okay? Which basis I'm going to use? Okay, so okay, let's call it CJ PJ. Sorry, so now I have J both on the right and on the left. Okay, so let's call this K. Okay. Okay. So now I'm going to insert this kind of decomposition in here. I'm going to look at one of the terms for one specific J. Okay. So maybe I should have an index J here, because each Kj has a different decomposition. Okay? So I'm going to do sum over A, okay? Sum over, okay, I need two indices, so K and L, okay? PA, PK, PA, rho, PA, PL, PA. And then I have coefficients, which are A, J, K, L, and I have these coefficients C, K, J, and C, L, J. Okay? Okay. So now I know what to do with this triad, right? What is this equal to? Right. So it's the same thing we saw before, right? So it's a sum over. I'm not allowed to write here, so let me just move this. Okay. So as we saw before, this is a sum over J and K. Sorry. K and L. And A, minus 1 to the power A comma K. Okay, this comes from basically contracting this tree. Okay, minus 1 to the power A L. And then I have basically P K rho P L. Okay? And then, yeah, I have the coefficient. C, K, J, C, N. Okay? So far? So now there's two different cases here. Okay? First case is that K is equal to L. That's already good, right? Because that's already Pauli channel. I have K and L are equal. So that I don't have to worry about, right? You with me? Okay? So the question is, what happens for the terms for which K and L are actually different? Okay? So I want to show you that basically, if K and L are different, the sum is equal to 0. Okay? So for K equal to L, the sum, not equal to L, the sum is 0. Okay? How do we see this? Yeah, there is cancellation here, exactly. And it comes about from a very simple fact. So I claim the following claim. This function from the Walsh-Hadamard transform, okay, have the following nice property. Okay, so if I multiply 2, what is it going to be equal to? Exactly. Not K minus L, but A times K times L. And what I mean here is that this is basically tells me about the commutation relation between PA and PK, PL. Okay? This is clear? This notation is clear? Okay? So this thing is going to be minus 1 if A and KL anti-commute, and PA and PK, PL. This is one operator. Okay? This is going to give you minus 1 if those two things anti-commute, and 1 if these two things commute. Okay? And it's very easy to see why this is the case. Okay? Because if I just compute the commutation relation of PA and PK, PL, right? So I need to commute this PA past these two operators. Okay? So what do I get? So either PA, first I commute PA with PK. I get minus, okay, maybe I should say first, this is equal to minus 1 to the power A, K, L. This is my definition, basically. PK, PL. This is by definition, this is how I define this quantity. Okay? So I'm commuting this operator with PA. This whole parenthesis with PA. and this I get minus 1 to the power a comma kn. Okay? Is this clear? This is just how this thing is defined. Okay? This is definition. Okay? And now, let's compute what is this commutation relation. Do it here. Okay? So if I just compute it, then, right, let's commute PA and PK, PL. So you see I have to commute first PA past PK, right? I have to do two commutations, one first here and then here. So first I do the first one, it's minus 1 to the power AK, and then I get PK, PA, PL. This is the first commutation. And then I do another one, and I get two of these two factors. Okay? This is the second commutation. Okay? So now you compare this with this definition. Okay, and you see that this is exactly what I wanted. Right? So now, if I look at the terms with k different than j, I see that I can, basically, for all the terms, if you want, I can replace this with minus 1 to the power of a. Okay. So now, but now, for this, let's fix k and l. Okay, now I have this sum over a. But so basically now I'm summing only on this number, right? This is for a fixed k and l. I'm summing over these numbers. This sum is equal to 0. Why? Think about Pauli's, right? X, Y, identity X, Y, and Z. Each Pauli operator commutes with exactly two other Paulis, right? For if I take I, X, Y, Z, okay, then I get that basically this sum, right? So for example, Z would commute with I, but not with X and Y. Okay? I commute with everything, but then I also have, I don't do anything to mine. Okay? So basically, this sum is 0. Okay? And there's no off-diagonal terms. Okay? So I've killed all the off-diagonal terms, and then, so K is equal to L. Okay? And then I get my Pauli channel, so K has to be equal to L, and then lambda tilde is just a sum, okay, over these numbers CK squared, CK squared, minus 1 to the power A K. Actually, I don't need this. Minus 1, this actually cancels. And then PK rho PK. This is my twirl channel. Okay, this is what we got from this calculation. Okay? No, because Yj. No, right. So you're right. So for each one of these j's, yeah. Thank you. So j, sum over k, and then right. But this happens for each one of these j's separately. Okay. So it's just a big sum over these Paulis, and I can lump these coefficients together. Okay. So is this clear? Okay, so by doing this randomized compiling, basically by applying random Paulis before and after the gate, I force my noise channel to be a Pauli channel. Okay? And this is what I can do practically when I run any quantum circuit. I can replace my quantum circuit with a distribution of quantum circuits in which I add random Paulis before each gate. Okay? So if I actually want to apply now a C naught, yeah. Any noise channel after I twirl it is going to be a Pauli channel. Yeah. It's very strong. It's a very strong statement, and this is why it's a very useful method. What?
But if twirling is not, if lambda tilde is not your noise,
but it's my noise after I twirl. So if you think about the twirled gate, okay, if you think about, so I have my gate, okay, so this is my C naught, and this is my noise channel, and then I added my random Paulis before and after. Okay, so if you think about this distribution of circuits as my effective gate, then the noise channel is Pauli.
But would this be dominated by the channel in the Pauli?
No. So, okay, so thank you. That's a very, so everybody understood what Yossi is asking? Okay, so this is a very important point. Let me just I'll return this in a second, okay? So for now, I'm assuming these Paulis are done perfectly, okay? And in this case, I can just take this, replace, instead of applying, when I do my experiment, I run the circuit many, many times. Instead of applying my C naught in a particular location, I actually, each run, I apply a different circuit with different Paulis. Okay, so each shot of the experiment, each experimental shot, I randomized over these Paulis, and I do a completely different circuit where I put these random Paulis. Okay? In practice, this is not very practical because the controllers that send pulses to the quantum computers, they take some time to recompile, to turn these instructions into actual pulses. So you sample from this distribution instead. But this thing converges extremely fast. I don't want to discuss now the convergence of this, but you don't have to sample, exponentially many instances in order to converge. It converges extremely fast. Okay, but if you forget this comment, basically you could, in principle, every experimental shot in your experiment, you can just use another instance of this random distribution. Okay? Questions about this? Is called randomized compiling. So just one thing about, so I so far I sweeps under the rug. So far I discussed, when I did this calculation, I only discussed the noise channel, so I forgot about the gate, right? So I kind of assumed its identity. But the situation is not very different if I actually have a gate here, if it's Clifford, right? Because I can always commute. I know how to commute this Paulis through the gate, right? Because it's a Clifford gate. So I can just commute them here, and then I know exactly which Paulis to apply here and here. So I can twirl, basically, the statement is that I can twirl only the noise. I can basically effectively do this. Okay? Is this clear? Okay, so I basically now, remember we had our noisy G. Let me write it like this. It was equal to G times lambda. Okay? Now I can write my noisy G as G times lambda tilde instead, where lambda tilde is a Pauli channel. Okay. Good. So I showed you how to turn basically every Markovian noise channel in your device into a Pauli channel, and this is very useful. So the next thing I want to describe is, I have to answer Yossi. So Yossi, what? I didn't. But okay, I assumed for now that these Paulis are perfect. I didn't assume that they're noisy. In practice, what's happening in the actual quantum computer is that applying single qubit gates is a much cleaner operation, so much higher fidelity operation than applying, for example, a CNOT. Okay, so there's at least one order of magnitude separation between the fidelities. But even if if you're not happy with that, you can show under some conditions that you could even use noisy Paulis for this. But this I'm not going to discuss. Okay, there's some conditions under which noisy Paulis are also okay. Okay? Okay. Questions about this, randomized compiling? Very useful method. So whenever you run quantum circuits, you should run them with randomized compiling. Yeah.
How do you transferring the J sum?
The J summation. Yeah, it depends on it doesn't matter. So again, this is a description of the noise. I don't care how many terms it has, right? It's just a description of the noise. But in principle, the J, if you remember where it came from my original Pauli channel. So having cross operators, and then each one of them is I use an expansion. Okay? But it doesn't matter how many terms are in this expansion as long I don't, this is the description of the noise, okay? As long as I can actually characterize this noise, then I'm happy. The number of terms in the noise, yeah, the number of terms I would need to characterize, I don't care about these numbers because in the end, there is some effective number here if you want, right? What I really care is the probabilities in the Pauli channel. Once it's a Pauli channel, if I want to characterize it completely, I just need to know these probabilities. There are exponential number of probabilities in a large device. Characterizing them is, of course, something would take exponentially long. But if you assume some basic things about your circuit, for example, has local interactions or something, then you can cut down considerably about the number. Okay? So you end up with some polynomial number of coefficients, or maybe even something that doesn't scale with systems. Usually polynomial number. Okay?
Yeah, but the probability may be high, but then you replace your noise channel with below.
No. So the probabilities are no. So no. At first, it cannot be one. This is a probability distribution. Okay. So you're asking whether I've deteriorated the fidelity of my channel. It could be that it changes the fidelity a bit. I don't want to discuss it exactly now, but if my Paulis are perfect, then the fidelities before and after the twirl are almost the same. For small noise, the fidelity before and after the twirling are almost the same. We can compute this, but let's not do this right now. Okay, so you can trust me here. Yeah. How much?
You have 8 more minutes.
Yeah.
And you promised to tell us about mitigation.
Yeah. So, but first, I just want to say something about characterization. So now I need to know how to characterize this channel. Yeah. There's some generalizations to twirling non-Clifford. I assume that the gates are Clifford, but it's enough because my noisy operations are usually, if you think practically, my noisy operations are the 2-qubit gates, or they're C-notes, so I'm happy to do this only for Clifford gates. Okay? So I don't lose anything. Okay? Yeah.
You mentioned confirming when you're actually working with linear algorithms.
Yes.
This is for
Yeah. Let me. I'll try to get to that, but I have 8 minutes. Okay. Yeah, there's a lot of gaming into this. Okay. There are several gains. I'm going to discuss one of them. Is this error mitigation thing, but actually, this is good for several things. It also effectively removes coherent errors. I can't explain right now why. Okay, it cancels coherent errors. So this is good for many, many things for improving the fidelity of your gates and mitigating the errors, and for characterizing them. Because now, as we said, now we could do this amplification. Because now I could take a noise description of the whole device, basically, and raise it to the power n, right? And I'm happy to compute the result, right? Because, as I said, this is a classical computing Pauli circuits with Pauli noise is a tractable computation for any n, basically. Polynomial computational task. Okay? So now I can do something called, I don't know which item I'm here now, 6 or 7, but I could do something called cycle benchmarking. And cycle benchmarking, what it is really applying this noisy twirled. Okay, this is a twirled gate in some sense. Okay, this is not equal to this. This is a different noisy gate. Let's put it. So it's a twirled gate. Okay. So what it does, what cycle benchmarking says, it says, remember it was good before to apply the gate n times in a row to amplify the signal. So now just apply your twirled gate, your G hat, n times in a row. Okay, so do a circuit like this. So basically, randomized benchmarking would be prepare some state. Okay, prepare some state. Maybe with some single qubit rotations. Okay, and then apply the twirled version of your gate. This is my 2-qubit gate. Okay, this is. So apply the twirled version of the gate. This is the noisy, okay, gate, and this together, this whole box is my G hat. okay? And now I'm randomizing over these Paulis, okay? And this is my noisy, this is my noisy CNOT, okay? And I'm putting Paulis before and after, with randomly as we discussed before. And I'm going to do this n times. Okay, so I'm going to do this n times. So this is again applying the same operation. Okay, and then I'm going to measure in some basis. Okay, and that's it. So, and then I'm going to basically directly obtain the coefficients in my Pauli channel. Okay, how does this come about? So let's, for now, this is clear. So the protocol is clear. I just do apply G hat n times. Basically apply G hat n times. Okay? And then prepare some state and measure some state. Okay, so let's take an example. Okay? I don't know. Suppose I want to know, remember, my goal is to know lambda. Okay, so let's do a 2-qubit kind of experiment. Suppose I want to know, I don't know what, lambda xx or something, okay? Or maybe two different, lambda xz. This is the term in the Pauli basis that has x on the first and z on the second. Okay, I want to know, sorry, I want to know this coefficient, sorry. This coefficient, okay? Remember there are these coefficients lambda, which are the diagonal elements in the matrix lambda. Okay, so what do I do? Okay, I'm basically going to prepare some state, which is basically, I'm going to prepare a plus eigenstate of xz. Here it is. Okay. Okay. And then I'm going to apply my g n times, as I wrote there. Okay, and then I'm going to measure the expectation value of xz. Okay, and then okay. So for now, I didn't say this. For now, again, let me assume. It's one thing I should have said. Sorry. Let me, for now, when I do this calculation, let me assume that my G is identity again. Okay, that the 2-qubit gate is the identity gate. For a second, because I'll soon say something about the CNOT. Okay, this just simplifies the calculation. Okay, so the perfect gate, instead of being a CNOT, is just the identity. Okay, so now, yeah.
We have only diagonal lambda?
Yes, we only have diagonal. So remember this, again, this matrix lambda, when I write it in the Pauli basis, the matrix, okay, meaning is 1, and then it has lambda, sigma, sigma A, sigma B, all different lambdas, okay? And this is there is a relation between these lambdas and the probabilities of the Pauli channel. So I'm now measuring this. These are equivalent because I can transform between them. I'm now measuring these numbers. It's a diagonal matrix, as we said before. Okay? So I want to measure, if I know all of these numbers, then I know the channel precisely. Okay? So this is what I have to do. And then I have to basically average, take the expectation value over all possible Pauli randomizations. Or again, as I said, this converges extremely fast. Okay? So, but in principle, I'm going to take the average over all possible randomizations, inserting Paulis, take the expectation value of the quantum measurement. So xz is, this is a +1 eigenstate of xz. So basically, this is equal to, this is equal to, this is applying, that's this g hat. So this is basically equal to trace xz d to the power n, or if you want xz g to the power n acting on xz. Okay, right? But we know that this is a Pauli channel. So what it does, this is right. It's diagonal in the Pauli basis. So what this gives me is just lambda xz to the power n times. That's it, basically. Okay? I'll say, give me 2 minutes, okay? Okay, so now by doing this experiment, I've extracted all these lambdas to the power xz to the power n, and then I could just measure them, and basically do a fitting and obtain those lambdas. How many rings do you actually have?
Yeah.
Okay, I don't know, I'm out of time.
We're out of time, and we have a bus after the coffee break and 2 lectures, we have a bus. So.
Okay, so I could be done here. Yeah, if anybody's interested in knowing about how to also mitigate, once you know these channels, right, there's a kind of a method to basically invert them. Okay, so basically, if I know the channel, I can think that what I want to do is basically apply the inverse of this channel. Okay, but the inverse of this channel is not a physical operation, but I could basically sample over circuits which look as if I've applied the inverse of this channel. And this is called, in the literature, this is called probabilistic error cancellation. So if you want to search for this, you can see exactly what it is. But what it basically boils down to is take your lambda. Once you've characterized it, write lambda minus 1 on a piece of paper, and then apply lambda minus 1. But applying lambda minus 1 is tricky because it has a very big cost in sampling, in something called sampling overhead. The number of times you have to sample the distribution of circuits. Okay?
And this can be done offline, I mean, with classic computer, or this has to be done again on that?
No, you do some post-processing on, so basically, if you give me to write down one equation, you're down?
Okay.
So suppose I wanted to apply a unitary gate U, okay? This is my perfect gate. This is, for example, my C note or something. Okay? But what I have at my disposal is the noisy U, okay? And maybe I could also put some Paulis before or after, maybe a reset gate. I could do all kinds of things before and after this U. So I have, instead of this C naught, I have a bunch of noisy operations that I could do. And I characterize all these noisy operations because I just showed you how to characterize everything, okay? So then you basically need to solve, an equation like this. Sum over alpha, P alpha, okay? There is, the claim is that you could always write your perfect, if you have a large enough set of noisy operations that kind of spans the whole operator space, okay? Then you could solve this equation. Your ideal C naught is equal to a sum over these things. These are my noisy operations, okay? This is just plus or minus 1, that you can compute effectively. And the sum over alpha, P alpha, are equal to 1. So this is called sometimes a quasi-probability distribution because it has these negative numbers, okay? The thing that, so if I did not have this gamma, I would be extremely happy. Because all I need to do now is sample from these noisy operations, compute the expectation value for each noisy operations of whatever expectation value I want, and just combine them and go home happy, okay? But the problem is that I have this gamma. And this gamma tells me that basically it increases the variance of my observables when I try to measure. Because now it tells me that if before I needed to measure something to accuracy epsilon, now I have to measure it to accuracy, now I have to measure it to basically accuracy of epsilon over gamma to cancel this gamma. Okay, so I have to sample more times. Each one of those instances has to be sampled more times in order to basically cancel out this gamma. And this gives me basically an exponential overhead because for each gate in the circuit, I have to sample more time. Okay, so there's an exponential overhead that comes with mitigating this noise. But, it could completely, in principle, completely remove the noise. The relation to the Pauli channel is that this relation becomes simple and doable in the case where channel is Pauli. So this is the relation between Pauli channel. This I do not have time to discuss, but if you have a Pauli channel, then you can effectively solve this equation and then basically cancel the noise from your expectation value.
Let's thank Netanel.